make you host if okay. Host. Try now.
Yes.
Perfect. Okay. See you later.
Bye.
Bye.
Okay. So sorry for this, but I guess we reached the time limit for the call, for the conference. Use the link that you have to enter again the conference, the Teams.
Ricardo, can I ask you a question?
Yeah, sure.
In the example just before, you were explaining how the function is mapping to the balance or to the constant, and I think I understand the balance case, like you map an 0, 1 to the order n into 0 or 1. So what is the case of the constant? If you have a like 1, 0, 0, 0, how does it map to a constant if the output is 0 or 1?
No, but okay. It's constant. The function is constant when whatever input you give returns always the same answer. Okay, so of course you have two possibilities. Okay, so you can say it's a constant if on all inputs the function returns 0. This is one case, one function. A different function that is still constant on all inputs return every time a 1. Okay, so these are two. So these two don't mix now in the same function. One function is okay, always 0, and the other one is always 1. But they are two different cases that you can have. Okay.
Okay, perfect. Perfect. Thank you.
No problem. Okay, let's go on. Okay, I hope, I don't know how many people there were before the crash, but I hope we are almost, so we are all here again. So we were at this point, okay, we have this function with this circuit, this is the JOS algorithm. Okay, the u of f is the function that evaluates the f that we want to understand if it is constant or balanced. U of f is defined this way, like we've seen before. Okay, basically it takes in input all the qubit state associated with these n qubits and outputs its result. Okay, where x in this case is an n qubit register, okay, and y is this one. Okay, let me go to the chat. Okay, let's go with so let's try to understand how this algorithm works. Okay, let's do this step-by-step analysis. Okay, in the first term, okay, you have the initial inputs. Okay, they are 0, 0, 0, 0 n times that you can write in this way, and on the second register there is a 1. Okay, then you apply h times 0 n to the first register and h to the second one. Okay, so, and this is what you want to do. Okay, what happens here? Oh, okay, we can write this in this way because we have seen it before. Okay, let me. You probably have it in front of you, something like that. So you should have in front of you. Okay, this became a mess, but I can fix this. Okay. You should have this in front of you, more or less. Okay, you have this in front of you.
We're still seeing your regular screen, not what you're writing on.
Okay. Yeah, sorry. Right. So, okay, you should have this in front of you. Yeah. We have seen that this also becomes 1 over square root of 2 to the n, sum over x. Okay. So you should have this in front of you. So this is what the effect of hn to 0n, and this is something that we already know is the effect of h to 1, which gives you the minus state, so 0 minus 1. Okay. Then what happens? It happens that you want to apply the circuit, the unitary that evaluates f. Okay. Are you with me so far? Okay, is it okay? Write in the chat if everything is fine. Okay. So if you're lost, please write, or if it's okay, write yes or thumbs up. I don't know. Okay, so let me go on. So you apply the u of f. So what you are doing is the following. Okay, you basically split this the thing inside the parentheses into 2 terms. Okay, this is the first term. This is the second term. Okay, you just multiply this one outside the parentheses with the first term inside and with the second term. Okay, plus you apply u of f. U of f is the one here, defined here. So what does it mean? It means that the result will be, so in this case, when you have x0 and you apply u of f, you have x0 plus f of x. In this other case, when the second register is in 1, you get x1 plus f of x. Okay. Again, you can rewrite this in this way. Okay, basically, okay, maybe it's easier to see it from here than to this term, this passage here. Okay, when you apply u of f, you transform this qubit register into f of x plus 0 minus 1 plus f of x. Okay. Of course, 0 plus f of x is again f of x, and we're left with this state here. So are you with me so far with this state? So at this point, after the application of u of x or u of f, you are in this state. Okay. So write yes. I want. I understand which is the x. X. Okay. X is what happens when you perform hn on 0n. It's what we wrote here. Okay, is what you should have in front of you. So when you apply, let me write it better. Hn to 0 and you get this one. Why? Because because h of n is the one shown here, and we have seen before that this could be a general way of writing h of n. Okay. So x is basically when you do h n 0 n, you do you obtain a superposition of all the bit strings. So it's something like 1 over square root of 2 of n of what? 0, 0, 0, 0, 0. Oh, sorry. Plus 1, 0, 0, 0, 0, plus, and so on until you get 1, 1, 1, 1. So, sorry, let me write it here. So this is the meaning of this thing here. Okay. Okay, so let's go on. So we said, okay, we are at this point here. Now look at the second part of this quantum state. Okay, you have f of x that, by definition, f of x is a function that returns an output that is either 0 or 1. So you have two possibilities. When f of x is 0, then this term becomes 0 minus 1. When f of x is 1, this term here becomes 1 minus 0. So when f of x is 0, you get the state here. When f of x is 1, you get a minus sign, because you have 1 minus 0. How can you write this in a smart way? You can write it in this way. So you can leave inside the parentheses 0, 0 minus 1, but you multiply everything by minus 1 to the f of x. In fact, when f of x is 0, you get this result, that it's what you want. When f of x is 1, you get minus 1 here, which reverses the order, okay? So this is a trick. Okay, I think this is pretty trivial. And okay, we have this state, and we reached the final Hadamard gate applied on the first n qubits. But look at the second register here. We discard it. So we basically don't care about what happens to the second qubit registers, which is this one. And we only look at what happens in the first register. Okay, let's apply h of n. So h of n is this one. So this is the initial state that we have. When you apply h of n, what we get is okay, what we get is that these two together multiply is a scalar product, and you get Dirac delta, sorry, the Kronecker delta, which means that zeta, every time you see zeta, it becomes x. So you can write everything, so you can rearrange everything in this way. So basically, it's, as we said, z becomes x. So this becomes x. This becomes x times x is 1. These two in blue become 1. So it's a scalar product, I mean, they become 1. And you have this term here, which is minus 1 y times x, which is this one, plus this term here. Okay, So since they are binary string, they not add, normally they add modulus 2. 2 times m multiply in this way, okay? It's quite easy. Just remember that this is a scalar product. You do the scalar product between z and x, and gives you 1, and gives you also that z becomes equal to x. And you can rewrite this in this way. You can then exchange the order of the simply say, split the two summations, and you can write it in this way. So if you look at this final state here, basically it's a state, it's a quantum state that you will write with y having the thing inside the parentheses, being your probability amplitude. So basically, when you measure y in the last step, you get some string with probability equal to this term modulus square. So actually, no, you get some outcome at the output here when you measure with some probability that is exactly this term inside the parentheses square. Okay, let's look better at this. So are you with me so far? So okay, the goal of the first 2h gates is to get the target state. Apply UF, it's only depending on the first qubit. Okay, let me re-go. So you mean here, so the first h, the first 2h, so this one and this one, basically the aim here is to put everything in superposition in the first n, for the first n qubits. So these are n qubits, okay? If you remember what we said before, this is not a qubit, this is a list of n qubits. To each one of them you apply Hadamard, okay? So the first one is to put, the aim of this one is to put everything in superposition. The second one is to store the result of the U of f on all inputs. The all inputs are in superposition. So the first register tells you which are the inputs. The inputs are all in superposition. The second register here gives you the answer, but the answer to something that is in full superposition. So also the answer will be, the answer also depends on the superposition on these terms here, because as we have seen here, okay? So in some sense, what you're saying is correct, but in such a way that the last qubit depends on on f of x calculated on the first register. Okay. So we were here. Okay. So what happens if f is constant? So I recall you that f is constant when returns 0 or null inputs, or could be that f returns 1 or null inputs. So one of these two possibilities. What happens if we substitute 0 or 1 here? No, sorry. Imagine that we want to calculate the probability of finding the string 0000. So the probability where the string where y is a collection of zeros. Okay, the probability of getting this string is, if you look here, is basically so y times x goes away because of this choice of y, and you are left with f of x in the exponent alone. Okay, again, if f is constant, which means that f of x is always 0 or is always 1, minus 1 to the 0 minus 1 to the 1 with everything square always gives you 2 to the n over 2 to the n, which is 1. So what does it mean? It means that the probability of finding y, which is the string, the 0, 0, 0 string, is 1. So what does it mean? It means that when I measure the first n qubits, if the function was constant, I will get in output all zeros. So if I measure and I get all zeros, I am sure that the function is constant. Okay. The other case is when f is balanced. When f is balanced, what happens? It happens that the opposite. So the probability of measuring the string with all zeros is 0, because in this case, here, look at the summation here. For half of the inputs, we have 1. For the other half, we have 0. So we have a summation of minus 1 to the 1 plus minus 1 to the 0. So because, and the since the summation split in 2, okay, which means split in, so we have 2 to the n terms. Half of them give a positive contribution, half of them give a negative contribution, which means that the summation becomes 0. And so the probability of finding state, this of measuring a bit string of all zeros, is 0. So finally, okay, so how many evaluations of the queries of the functions of this u of f are needed in this quantum algorithm to determine with certainty if the function is balanced or constant? Just one, because if I run the circuit and I measure all zeros, then I know for sure that the function is constant. If I measure instead and get at least one in the bit string in output, I'm sure that the function is balanced. Okay. So, but the way I do it is I run the circuit just one time. And this is in contrast with the classical query complexity, which was, that we've seen before, it was 2 to the n, something that goes like 2 to the n, okay? And this is the power of, so in this way, you exploit quantum parallelism to the maximum level, okay? I think we have the pause now, the pause. But first of all, tell me if you are with me so far. Tell me if, is it clear the Joy-Zosa algorithm so far? Or do you want me to explain more something about it?
Okay. Seems that you've been very clinical.
Okay, thank you.
Can I
Okay.
maybe ask
Yeah,
one
yeah,
question?
sure. Sure.
Yes.
So about the practicality of this algorithm, because you have this UFF in this gate, but in reality, in the quantum computing, there is no such thing as a UF gate, isn't it? So what is? I would say I don't understand exactly the purpose of this, unless it's just a thought experiment on how it's possible to parallelize this kind of thing. Is that correct?
Okay, U of F, you can create a function that is U of F in a quantum computer. Maybe the application, let's say real world application of this algorithm is a bit hard to find because okay, you have to find a function. I mean, is not you don't often have a real world problem where at the end the task is to try to understand if some function is balanced or constant. So it's not very useful algorithm, but in some ways, so, I mean, using gates, you can definitely construct some function U of F, okay? And we will see it after with, for example, with the Qiskit in the afternoon, and I will exactly explain this algorithm here. And we see that you make a choice of U of F from the beginning, and then you can run this quantum algorithm. And U of F is going to be something like control knots, so something like this. But the idea is that it's a combination of gates that takes an input, some string, and returns 0 or 1. Okay, and they do it being constant or balanced. Okay, so you can definitely construct a circuit that implements your U of F. Okay, is it clear? Okay. So I think that, yeah, we can have a break until 11:05.
Exactly. See you at 11.
Okay, see you later.
See you later. Bye.
Bye.